Good morning, everyone. Today, we are very pleased to have Professor Yushan Yan to give a seminar jointly sponsored by IAS Institute of Energy and the Department of Chemical and Biomolecular Engineering. Some of you may have known Professor Yan because he was here last year when we organized a small workshop. He gave a lecture. And for those who do not know him, I would like to take 1 or 2 minutes to give a brief introduction. So Professor Yan obtained his bachelor degree from China University of Science and Technology. That's in 1988. And then he went to Dalian Institute of Physical Chemistry, and he worked there for 6 years. And after that, he joined the Caltech and got his PhD from Chemical School of Chemical and Chemistry and Chemical Engineering from Caltech in 1996. And after that, he worked for industry, and that is the company called Allied Signal Incorporated, and he worked there for 2 years. He's a senior staff engineer, and then he joined the University of California at Riverside as assistant professor and promoted to associate and then full professor and university scholar and University of California presidential chair. And also during this time, he served as a departmental chair from 2008 to 2011. And after that, he moved to his current position, that is the Distinguished Engineering Professor and Associate Dean for Research and Entrepreneurship of the College of Engineering at the University of Delaware. And Professor Yan is an internationally recognized scholar. He was elected a fellow of the American Association for the Advancement of Science and recognized by the International Zeolite Association with the Donald Brick Award in 2010 for his stellar thin film research. So he was one of the 37 awardees in the U.S. Department of Energy's ARPAE Open 2009, and also one of the 66 awardees in the Open 2012 for his redox flow battery concept. So he has been an inventor on a number of issued or pending patents, some of which were licensed for to form startup companies. And he has been widely cited in the scientific community with total citation close to 10,000 and H index about 50, and extensively covered by the media, including New Scientist, Business Week, CNN News, Materials Today, MRS, and Chemical Engineering Progress, and China Press and Chinese Daily News, because he is also very actively involved in joint research with Chinese universities, particularly with Zhejiang University. So let's welcome Professor Yan to give us the seminar towards the distributed renewable electrochemical energy and mobile system.
Thank you, Professor Chen, for the very generous introduction. I think this is the longest introduction probably I ever get. Before I begin, I'd like to thank you all for being here and thank the faculty for the opportunity to come. I'm very honored to be here to introduce to you some of my work and toward the distributed renewable electrochemical energy and mobility system. In order for this system to work, we've been studying several devices like fuel cells, electrolyzers, and flow batteries. And today I'm going to focus only on fuel cells. And in order to make these devices work, we've been studying electrocatalysis and polymer electrolytes and electrochemical interfaces. And today I'm going to focus on electrocatalysis and polymer electrolyte. I took this as a general seminar. I'm not sure that's the best assumption, but this is the chart I've been enjoying reading for the past 15 years. It has a lot of information about the United States energy portfolio. It tells you where the U.S. gets its energy, such as solar and hydro and wind. I'll tell you, many years ago, these things don't even make it onto the chart because the amount is just so little. And it tells you where does the energy go, residential, commercial, industrial, and transportation, and in what format. And instead of going through the whole chart, only 2 points I want to make here. Number one, as of today, 40% of the energy is consumed in the form of electricity in the United States. And we've been trying to electrify the transportation sector. So if we are successful, about 70% of the energy will be consumed in the form of electricity. So it's very important for us to generate electricity the right way. And electricity is mostly considered the most convenient form of energy by many. So how do we generate electricity today? So this is a chart I lifted out of the chemical engineering progress. We usually have a very big central plant where we burn fossil fuels like coal or natural gas. And then we go through this high voltage transmission. By the time we get to the customers, we lost about 70% of the energy. So the whole system is not very efficient. So this is the system we imagine for the future. This is electrochemical conversion based. It has several devices we've been working on, like fuel cells, electrolyzers, and flow batteries. Clearly, there are many other electrochemical devices that will be able to contribute to this system, but I'm only putting down the devices I'm working on personally. So you can imagine you have a solar hydrogen system. You take sunlight, you can produce hydrogen, and then you can use the hydrogen to power fuel cell equipped cars, or you can take the solar wind electricity, you use the electrolyzer to split water into hydrogen, and then you go through the same. Or you could have a flow battery for storing the electricity coming out of wind and solar. So today I'm going to focus on only fuel cells. So what we see is, a revolution is coming in the sense, today we have very centralized, large combustion-based power plant. And in the future, perhaps we're going to have very distributed electrochemical devices networked together. And this is very similar to the computing revolution we had 30 years ago, where we used to have the centralized mainframe computation. But then, today we have very distributed networked personal computers, including the cell phones we use every day. So what is a combustion reaction? Well, the combustion reaction is a redox reaction. So what is the key process in a redox reaction? It is the electron exchange. So you can see the fuel molecules in the combustion process lose electrons, get oxidized, and then the oxygen molecules will take in those electrons and get reduced. So the key here is this electron exchange. And the feature for combustion is the electron exchange is a direct process, going from the fuel molecules to the oxygen molecules directly and irreversibly. So this has consequences in terms of efficiency. And then if you burn fossil fuels like natural gas or coal or petroleum, you're going to produce CO2, which is not very desirable. Alternatively, you can have this electrochemical conversion. Here, we use proton exchange membrane fuel cell as an example. I'm sure you probably know this quite a bit already, but let me just to make sure. So here you have two electrodes, and on the anode you have hydrogen molecules coming in and losing electrons and get oxidized. And on the cathode you have oxygen molecules coming in and taking in the electrons and get reduced. So if you look at the overall reaction of a fuel cell process, it is still a redox reaction. The difference between this redox reaction and the one I just showed it to you before is the electron exchange is no longer direct from the fuel molecules to the oxygen molecules. In fact, we actually insert a polymer electrolyte literally into the process and spatially and physically separating the oxidation from the reduction so that you're forcing the electrons to go to the external circuit to do some work for you. So this is very, very key. This is the most significant difference between an electrochemical process and the combustion process. So by doing so, you have this indirect electron exchange, which is more reversible and leading to higher efficiency. And if you have a hydrogen source which is very clean, you can have zero CO2 emission. So this is good. So fuel cell technology has been working really well. In case you're wondering, that's me sitting in the latest fuel cell car by Toyota. This is a Mirai car. It's a wonderful car. I drove it. Really, really nice. It can drive 400 miles per charge, and the charge will take about 3 to 5 minutes. So when you get into the car, you don't really feel any difference between this car and my normal Honda Accord. So it's a very nice car. So what's the problem? Can we have this car, soon, everyone can have one? The problem is the cost and durability. So these are the two factors cited most by people. But for me, it's really just cost. So I consider if you can get the cost low enough, you can tolerate some durability problems. So we really need to make fuel cell cars cheap. So how do we do that? So it turns out the biggest cost driver for a fuel cell engine is platinum, and it's costing about $22 per ounce. This is old data, but today it doesn't change that much. So imagine if we can somehow take platinum out and put nickel back in there. So it's going to cost a lot less because nickel is about 0.1% of the cost of platinum. So how do we move from platinum to nickel? So let me share with you some of the technology milestones for fuel cells, and that would tell you how we can go about changing from platinum to nickel. So first of all, in 1839, this is how fuel cell principles were demonstrated. You have two platinum wires in sulfuric acid, and you bubble hydrogen on one electrode and oxygen on the other electrode, and you measure the voltage, and you get a voltage, and this is how the principles were discovered. And then about 100 years later, it was realized we don't have to use sulfuric acid. We can use potassium hydroxide. And once you make this very simple switch, you can use non-precious metals instead of platinum. You can use nickel for hydrogen oxidation, and you can use silver for oxygen reduction. So the question is, why didn't we spend the past 20 years or 30 years to work on this kind of technology? Instead, we really spend most of our investment on this proton exchange membrane fuel cell. I think the answer is actually quite simple. We never really wanted to play with liquid electrolyte, be it acid or base, because liquid electrolyte, they're very corrosive if you touch them. They're going to burn your fingers. They're going to cause corrosion problem to the component, the containers. And also it's harder to make a device which is more compact if you're dealing with liquid electrolyte. It will be much, much better if we have a piece of plastic like the kitchen, food wrap, serving the electrolyte between the two electrodes. I think that's when DuPont came up with this wonderful polymer, Nafion. I think the field kind of converged to this proton exchange membrane fuel cell because Nafion is a wonderful proton conductor, very conductive, and it's also very stable thermally, mechanically, and chemically. So that's just wonderful. So I think everyone, probably everyone, including myself, thought that was it. So let's just do proton exchange membrane fuel cell. And but it turns out, as long as you stay with acid, be it liquid or solid, you're going to need platinum. You can reduce it. It looks like it's necessary to have some platinum in there. So the idea here is, what if we can make a Nafion equivalent? Literally, it's a polymer, but it doesn't conduct protons. It's only conducting hydroxide. So if we can do that, maybe we can have a fuel cell that can take advantage of the solid electrolyte as well as the basic or alkaline environment, so we can work with non-precious metals. So that's the idea. So this is what we call hydroxide exchange membrane fuel cell, because you need hydroxide to go from one side to the other. When we published our first paper in 2009, we insisted we call this hydroxide exchange membrane fuel cell. And I think there are many other names out there. And I think it's starting catching on right now. I think I still believe this is the right name for it. It literally took me a lot of time to think what name I will give it to this technology. So I think HAM fuel cell eventually, I believe, is going to win out. So when we get started thinking, okay, we want to do this hydroxide exchange membrane fuel cell, what could we do? So we went into the literature and started searching, does any HAM exist? It turns out anion exchange resin or membrane has been there since 1960s. So anion exchange resin, meaning you have this cationic group attached to the polymer. You put an anion in there. You can use any anion, so like chloride. But if you change chloride to hydroxide, that becoming hydroxide exchange membrane. So it's there. But the problem is they are all quaternary ammonium based. So you have this nitrogen sitting in the center with a positive charge. And this turned out to have low conductivity and, more importantly, low stability. What is interesting is, as a PhD student, I used to do a lot of zeolite synthesis. I actually use quaternary ammonia as the template to make zeolite in base environment. And I knew it's just not very stable. So life has a very interesting, circle. So what we came up is this quaternary phosphonium with some very specially designed side groups. So this is not nitrogen anymore, it's a phosphorus. And we have this very big side groups. It turned out to be very, very important to have these side groups with this organic cation. So how did we come up the idea? This is really for the students who are here today. So the first thing we thought, ammonium, this is what we don't want to touch. We want to go somewhere else. But if you really look at the periodic table, the neighbor on both sides didn't seem to be possible. But if you go down, phosphorus was becoming a clear target. And we actually had another paper on sulfonium, but today I'll skip that. So let me just share with you how we came up with this phosphonium idea. So we did a lot of literature search and seeing what's out there. So we found this very old paper, older than I am, probably older than most of the people here. It's a very simple paper, and we were very excited when we saw this paper. So let me tell you what it is. The horizontal axis is the electron withdrawing capability of the side group. So when you study organic chemistry, there are organic functional groups, right? Some is pushing electrons to the benzene ring. Some is taking electrons from the benzene ring. This is the electron withdrawing capability. The vertical axis is pKa. So simply translated, when you climb this axis, you actually get more and more basic. So in order to make a good hydroxide exchange membrane, you need higher basicity. And that's why KOH, potassium hydroxide, is the best hydroxide conductor. Unfortunately, we just don't want to use it. So you really need high basicity. Usually high basicity means the cation allows the anion to dissociate easier, to let go. And that's very important. So what we saw was really just intriguing. So you have this organic amine, meaning ammonium, nitrogen-based. So you have no substitution, and then you have one substitution. So you have R, you have two substitution, you have three substitution, like primary amine, secondary amine, tertiary amine. So you see the basicity is actually going down. This is not where you want to go. But if you look at phosphonium or phosphine, very interesting. You have this primary phosphine, 1R, and then secondary phosphine, meaning two hydrogen atoms get replaced by a R, organic alkyl group, and tertiary phosphine, the basicity is actually going up. So this is the direction you want to go. So our imagination was, if you allow the quaternization, they may actually switch. You might have a basicity out of the phosphonium higher than ammonium. So that was very, very exciting to us. And then we asked the question, how stable is it? So there's another very old paper out there. It shows the study of the stability of this quaternary phosphonium. So you can see this is the phosphorus atom with 4 side groups. What they do is they try to put one substitution to this benzene ring and then started trying to degrade this one in KOH and see how fast the reaction goes. And the horizontal axis here, again, is the electron withdrawing capability of the side group. You put it on the benzene ring. And the vertical axis is the degradation rate. So you can see if you have a very, very strong electron withdrawing group, and the reaction is very fast. But if you started putting the very, very strong electron donating group like methoxy, and you can see the reaction rate is much slower. This is a log plot. So this is about 3 to 4 orders of magnitude of reduction of the reaction rate. So this is telling us methoxy group is very, very critical. So again, our very naive imagination was, well, 1 can do so much for you. What if we put 9? We might be able to really put this one down to the sub-basement. And the other thing, really, for the student, I want to make a suggestion. When you are given a topic, try to read some really old papers, and even far beyond your age. What I found was this is very, very beneficial. Our brains have been the same for a long, long time. Very often the problems we're worrying today, there is a solution already there. And these papers are really, really nice and easy to read. It's just only 2 pages. So it's rarely very, very long. So I think it's easy on you in terms of reading. So please do so. So we've been publishing several papers in this area. So this is our first paper showing quaternary phosphonium was a good ionomer, meaning soluble ionomer. And this is sort of my spare time interest. I like to design these figures. I don't draw it. I have an artist friend who doesn't know much about, none about chemistry, but he is really intelligent. So I work with him designing all this stuff. And I usually joke to him, I can't put my pen on paper because the moment I put my pen down, it's already not what I wanted. I can only talk. Yeah. And so this is our second paper showing we can turn this one into a membrane performing really well. And in case you're wondering, so this is a OH minus FC as a license plate, and this is a HEM FC as a license plate. This is too small for you to read. And then this is really showing, we get lucky, the polymers we chose have this van der Waals interaction, making it as a physical cross-linking and making the property better. So I'm going to skip. In case you're interested, you can easily find the citation. But what I like to do today is really sharing with you unpublished results. I think the papers are out there. You're able to find them easily and read them easily. I feel I came from very far away. I want to share with you some. It's not published yet. So ever since we got this quaternary phosphonium working, we have a number of questions we've been asking. How stable is it? We said it's more stable than quaternary ammonium. We had some data showing that, but we had never done a systematic study. The second question is, are the 9 methoxy groups necessary? I told you that was our imagination. 9 would be great, but maybe 4 is enough, maybe 3, right? That's another question, how does it degrade if it is not perfectly stable, right? The final question is, if we already know how does it degrade, can we come up a strategy to make it more stable? So this is basically the thesis of a PhD student of mine. She just defended about a month ago. So first, let me show you how stable is it. So we do this in a test. It's 80 degrees C. We have this KOH, but now it's KOD because we need to do NMR. And we have this model compound. So instead of working with a polymer, we actually have this organic cation, just like the one shown in the Jack's paper. And we have the base as a KOD. And we usually have a lot of excess of the KOD versus the model compound because we want to make sure the basicity doesn't go down as the lifetime testing go on. And we also added methanol in there because the moment you put methanol in there, you make this solution much, much more aggressive. It's actually more, it's tougher. So this is an accelerated durability test. And we have internal standard. We've done a lot of NMR. I'm not going to bore you with the NMR, so I'm actually showing none today. So I'm just hoping you trust me. So this is what we found. This is the horizontal, this is the time, the organic cation inside the solution, and this is the percentage of the cation remaining. So the red is our quaternary phosphonium with 9 methoxy groups. And this is the quaternary ammonium, the benchmark, the nitrogen one. This is the phosphorus one. So you can see, indeed, this one is more stable than this one. You may think this is of very little difference, but this is a very, aggressive test. So if you take the methanol away, the difference will become bigger. But nonetheless, it's more stable. So the next question is, are the 9 methoxy groups necessary? So we started saying, okay, what if we don't put any substitution? What if we put 3 methyl groups? What if we put 3 methoxy groups, but not 9? And I have a list of 6 methoxy groups, and we actually changed the methoxy groups to position, from paro, meta, author, and I'm going to skip all that in my student's thesis, just showing you these 3 simple molecules. If you look at the testing conditions, they're the same. So what we found was very interesting. So this is the number of hours of the test, and this is the percentage remaining, again, just like before. So what we see is, if you have no substitution, this one basically would just go bad right at the door. It wouldn't get out. And the other thing I want to point it out is this is a 20 degrees C test instead of 80 degrees C. So it's a much milder test already, and this guy doesn't even get out of the door. And then if you look at the 3 methyl groups, slightly better, but not by a whole lot. And if you look at 3 methoxy groups, it's already much better. So this tells us clearly the electron donation is very important for protecting the center atom, because methoxy group, as I showed it to you, is a much stronger electron donating group, because all three have very similar steric hindrance, because you have just only one group. So if you put all of them together, these are the three: single substitution or zero substitution, and this is our 9-methoxy substitution. You can see this is the lifetime, and this is the temperature. Usually higher temperature meaning lower lifetime. So this is, even at a lower temperature, is still much less stable in terms of time than this one at a much higher temperature. So that shows you 9-methoxy groups are necessary. And once again, we have a lot of more data than this one, but I think you get a point. The next one, how does it degrade? So now we know 9-methoxy is not perfectly stable. So how does it degrade? So it took my student Bingzi Zhang for a long, long time to figure the thing out. So now I'm just giving you the conclusion. So if you have the single substitution, the degradation mechanism is oxidation. So basically, you strip this side group away, and you put a double bond on the phosphorus, and you attach oxygen. So this becomes phosphorus oxide. So this is how the cation goes bad, become neutral, and fall apart. What we found was, for the 9-methoxy one, it goes through a totally different mechanism. So this is a little bit small, especially for people in the back. So imagine here with me, this is the methoxy group. So the first step is actually deprotonation. So hydrolysis, I should say. So when you have this KOH here, you turn this methoxy group into a hydroxyl group. So you hydrolyze this one. And then the next step is deprotonation. So you take the proton away, you form a O- here. And you have a P+ here, and this is a conjugated system. So you can have this ketone rearrangement. You form a double bond here, and then you take away the positive charge as well as the negative charge. So you can see, as soon as you take the positive charge away, this is no longer able to function as a hydroxide exchange membrane, because there's no charge for the hydroxide OH- to balance anymore. But the good news is this organic group never fell apart. It's still an integral group. It's just the charge disappeared. So we felt this is making us hopeful. So immediately the idea was, well, we can change it from this 9-methoxy group into this 9-methyl groups, because the methyl groups wouldn't be able to do this hydrolysis, wouldn't be able to do this deprotonation. So imagine, that might make this organic cation much more stable. So here is our results. So the horizontal axis is the how many days, and this is the percentage of cation remaining, and this is the quaternary ammonium, and this is the quaternary phosphonium with 9-methoxy groups. But we made a change in terms of the fourth group. We used methyl instead of the benzyl group. I showed it to you before. The reason is we couldn't make the benzyl group going in here. The steric hindrance is too big. But then the question is, what if we show this higher stability? And people question, is that due to this methyl? So we actually done this methyl to this 9-methoxy, and you can see it's the same stability. So you can see once you switch this one to 9-methyl, it's becoming much, much more stable. Actually, our latest data is like 200 some days, and still very similar stability. So this is the most stable organic cation available today. So this is our hope, for the future hydroxide exchange membranes. So now I'm going to switch topic and talk about catalysis, because if you look at a fuel cell, you need to figure out the membrane. Hopefully we had a solution now. And what about the catalyst, on the cathode and on the anode. One thing I want to point it out, when you do this catalysis in base, in alkaline system, the oxygen reduction reaction is not a problem. Although you may see many, many papers each year published in this area, I just want to tell you there's no problem there. Like carbon-based material will do as well as platinum. So there's no need to work on that, unless your goal is beat platinum by a large margin. Otherwise, you're just beating platinum or equal to platinum is not very significant. So the HOR, surprisingly, is the problem. It's very hard to deal with. So I've done some heterogeneous catalysis years ago at Dalian Institute of Chemical Physics. And if you talk to anyone doing heterogeneous catalysis, they will tell you hydrogen oxidation is the easiest reaction you will ever find. I mean, you don't need to do anything. But it turns out pretty hard here. So let me just simply say there's literature data out there. HOR on platinum is about 200 times slower in base than in acid. So this is very intriguing. Somehow, when you switch from acid to base, it's becoming slower. So the question is why? And how can we get a good non-precious metal HOR catalyst? Because this is where we're going, right? But we need to understand why here. And hopefully, by knowing that, we can get the catalyst we want. So let's look at the hydrogen oxidation mechanism. There are two elementary steps. Actually, there's a third one, but I'm just trying to make things a little simpler. So one is the hydrogen adsorption onto the metal surface. This is the TOEFL step. In heterogeneous catalysis, we simply call this dissociative hydrogen adsorption. So you have this hydrogen molecule coming in, split into two atoms. One atom will get onto a side, so you become hydrogen adsorbed. And then you have this Volmer step, which is the real oxidation step. So you have this one get oxidized to give up an electron, become a proton, give back the side. So these are the two steps. The point I want to make here is, if you take a closer look, hydrogen adsorbed is the key intermediate. So the expectation is you want to have the metal absorbing the hydrogen atom just of the right strength. If you do the adsorption too strongly, the intermediate will not want to leave the surface, making the reaction slower. Or you have the adsorption too lightly, and then the catalyst doesn't have the opportunity to influence the reaction, so you're going to have very low reaction rate. So the expectation is you're going to have this volcano plot. And the horizontal axis here is the hydrogen adsorption strength. The vertical axis is the exchange current density, or the activity of the HER reaction. So for this particular paper, horizontal axis is a DFT calculation. The vertical axis is the experimentally measured reactivity. And you can see all the metals here. Indeed, we have a volcano plot. So you can see platinum is somewhere sitting at the best place. And gold and silver are very bad because they don't absorb hydrogen as strongly as needed. So this is important. So the first question we asked was, do we have a volcano plot in the base system? So here we also do the DFT calculation. This is actually done in collaboration with Jingguang Chen. He does DFT calculation. And this is the vertical axis, is the HER exchange current density. These are the metals. So you can see we have roughly a volcano plot as well, and platinum is at the top. So this was good. Hydrogen binding energy appears to be still a very important parameter for deciding the reactivity. Now we ask two more questions. So if you look at the previous two studies, one is by Noskov and one is by us, both studies having the horizontal axis occupied by DFT calculated numbers. And DFT is a wonderful tool, can provide a lot of useful information, but doesn't take into account the solvent, like water. It doesn't take into account the electrolyte. It doesn't know if it is in acid or base. Has no information of that. So this is one shortcoming. And if you look at the pH, their work was in acid. Our work was in base. So pH 1 versus pH 13. And there's nothing in between. So this is another gap. There's no study in between these two extremes of pH. So what we wanted to do is we want to correlate the activity to an experimentally measured hydrogen binding energy for the first time. So that was the goal. So this is how we did it. This is the cyclic photometry plot for platinum. So the horizontal axis is the potential, the vertical axis is the current out of the disk electrode. And I don't know how much you know, this is a very standard electrochemistry technique. So imagine if you scan the potential at a certain point, you oxidize platinum, and you take it back, and you reduce the platinum back. And then at certain potential, you're going to have this under potential hydrogen deposition, meaning you're reducing proton into an atom, and that atom get onto the surface of platinum, and you form a monolayer. And the reason we call this under potential deposition because it occurs at a potential hydrogen is not supposed to be reduced. So this is higher than the zero potential. Usually at zero potential, that's by definition, you get your hydrogen out, but it happens earlier. Just because hydrogen really, really enjoys being on the surface of platinum. And then when you reverse the potential, you started oxidizing the atom on the surface, and then you do the discharge, turn it into a proton, gave up the electron to the electrode. So this is, you call this desorption peak. What I want to say is, it has been known for a long, long time in the electrochemistry community. The peak position here is actually related to the hydrogen binding energy. So this is known. But there was no rigorous derivation based on thermodynamics and absorption. So we did that. It turns out the peak position is indeed related to the hydrogen binding energy by a formula like this. So there's just an entropy difference. So you can see the peak position is literally the hydrogen binding energy. So what this tells us is, if you just measure the peak position, you already have the hydrogen binding energy. So this is very important. So once you know that, we started doing experiment. So we have a CV at pH 0, very acidic. And then we started moving the pH up to an acetate buffer, 5.0. So you can see the peak is moving to a higher potential. And then if you increase this one to 6.7, the peak is moving to an even higher potential. And then you just keep going, and then just going higher and higher. So what this tells us, when you move from acid to base, your hydrogen binding energy is getting stronger and stronger. So this is very, very important. And this is the hydrogen binding energy experimentally measured. It's not calculated. So does this make sense? So if you look at the volcano plot in acid, the reason I want to use acid because platinum has almost no overpotential in an acidic system. So platinum is sitting here, imagine, and now I'm showing you when the pH is getting higher and higher, the binding energy is getting stronger and stronger. So where the direction is going, it's going to go in this direction because this is a higher and higher binding energy. If you look at this, where do you expect the activity go? The only place for the activity is to go down because this is the trend, right? That's exactly what we saw. So now I'm going to show you the correlation. So the horizontal axis here is hydrogen binding energy going higher and higher. And this is the overpotential of either HOR or HER. So overpotential meaning if you have higher overpotential, the reaction rate is slower. So let's focus on HOR, which is of more importance to me. As the binding energy goes higher and higher, you see the over potential is getting higher and higher. So indeed, this is what we expected, right? What was interesting is, immediately we started thinking, wow, if you have platinum sitting here, you move from acid to base, and your binding energy getting stronger and stronger, the activity is going to get lower and lower. We saw that. What about gold? Gold is hanging out here with a very weak hydrogen adsorption. If we started scanning from acid to base, maybe this one will climb up, right? So I had a PhD student who started saying, let's try it. And so far he's been telling me, no, it's still going down. So it didn't go up. So we need to figure it out now. So now I'm going to tell you, we have certain amount of understanding already. How can we come up a non-precious metal catalyst? And I want to say, at the end of my career somewhere, if we can't get a non-precious metal, totally non-precious metal catalyst working, I'll consider it as a failure. I mean, the reason we took the trouble to move from acid to base because we wanted to get non-precious metal. If we can't get to non-precious metal, we just failed. So let's see if we can get there. So the first thing we did is, okay, hydrogen binding energy is very, very important. So can we scan through some non-precious metals? So you can see here, platinum 111 surface this is the binding energy. If you start with moly, it's very, very negative, much stronger adsorption, not very good. If you look at nickel, it's also much stronger, not good. But if you have a nickel moly, this thing is getting closer to this platinum hydrogen binding energy. And if you have the cobalt nickel moly ternary alloy, it's getting very, very close. So that was good. So this is nickel here. So we're thinking if you get this ternary alloy, maybe this would just go to platinum. And again, this calculation was done by Jingguang Chen. Yeah. So that's the beauty of being with a very large department. So I can find collaborators much easier. So here is our data. So if you look at the horizontal axis here, this is the potential, and this is the current density, and this is the HOR polarization curve. Basically, imagine if you have the potential going positive, and you have this HOR activity going higher and higher, at some point of time it's going to level off because of the mass transfer limitation, because you're literally having trouble delivering hydrogen gas to the surface. So the black lines here are platinum disk. And if you look at the red lines, these are for our cobalt nickel moly. And these catalysts can outperform platinum disk easily. And these are 3 different temperatures: room temperature, actually below room temperature, and higher. So you can see, indeed, we can come up with a totally non-precious metal catalyst outperforming platinum. So that was very exciting. And if you really go into the fundamentals, this is about 20 times the activity of pure nickel, but we're still only 20% of platinum activity. But we can increase the loading. So you can see this indeed moved up. But the question, the point I want to make here is, we had a lot of trouble making this nickel cobalt moly catalyst using wet chemistry, which just couldn't reduce these things very nicely. So eventually, in this study, we had to use electrochemical reduction, because you can literally get the potential down whatever you needed. So that was good in the sense we produced the catalyst we wanted, but at the same time, performance-wise, that's not manufacturable. Like, we can't use that method. So we really want to come up with a new catalyst. So this is our newest version. At some point in time, I need to submit a paper. So this is a nickel supported on nitrogen-doped carbon nanotube. And this is the TEM picture. And the reason we tried this, we also have calculation, which I'm skipping it today. And the other is the intuition. So when you have nitrogen-doped carbon nanotube, you have one extra electron on the nitrogen, which is going to be possibly donated into the nickel atom so that you can reduce the binding energy. So we have calculation which I'm not showing you, but let me just quickly say it appears this nickel supported on nitrogen doped carbon nanotube is much more active than the non-nitrogen doped or the pure nickel or the pure carbon nanotube. So this is very exciting, and this is a powder catalyst. What I want to show you, the last data point is the simulation. So this is not a true fuel cell test, at least not our line. So let me explain to you. So this is the polarization curve. The horizontal axis is the current density. The vertical axis is the voltage. If you look at this blue curve, this is experimental curve out of the 3M company. This is the highest performing PEM-FC, proton exchange membrane fuel cell. If you look at the green curve, this is our simulated polarization curve based on an experimentally demonstrated non-precious metal oxygen reduction catalyst and our nickel supported on nitrogen doped carbon nanotube. We only have rotating disk data. This is not in the MEA, so we know the Bartoloma, the potential current relationship. So I can do the simulation. So what you can see is the green curve can actually match the blue curve. So this is the important message. If you allow only 0.1 volt over potential applied on the anode on nickel, you can reach 648 milliwatt per square centimeter. This is here. If you can afford to have 0.15 volt over potential on nickel, you can actually get here. This is actually much better. I think I should change myself. The green curve is the PEM fuel cell. The blue curve is our own curve. You can see that this is very, very exciting to us. What this tells us is we really need to get our nickel catalyst more stable. We don't need to make the nickel catalyst more active anymore. If we could, certainly we'll benefit. But really what we need is just make it more stable. So now I'm just going to summarize. We believe, quaternary phosphonium is a really, really promising cation for hydroxide exchange membranes. I believe our 9-methyl phosphonium is the most stable one. The hydrogen binding energy is likely to be the sole descriptor for HOR reaction activity on monometallic catalyst. There's quite a bit of a debate in the literature right now about the role of hydrogen binding energy. So we have our own opinions, and there are some alternative explanations. We already have sufficiently active non-precious metal catalyst, but we just need to demonstrate more stable catalyst. And we feel hydroxide exchange membrane fuel cell are commercially viable based on the simulation. Since I'm a chemical engineer, so last year we wrote a review in the annual review for chemical biomolecular engineering. So in case the student have interest to take a look, this is sort of our vision or our view of the future. I think in chemical engineering, there's a lot of things we could do in this particular area. And then finally, I want to acknowledge the few people whose work was specifically mentioned today. So if you look at the original 9-methyl quaternary phosphonium work was done by a former joint student and later postdoc, and now a research assistant professor in my group, Shuang Gu. He is going to become a faculty shortly in the US. And then if you look at the 9-methyl and the degradation mechanism group study was done by my PhD student, Bingzi Zhang, who just defended about a month ago. She's going back to China, to Beijing Institute of Chemical Technology. And then if you look at the nickel moly cobalt work was done by my former postdoc, Wenchao Sheng. She is now at Brookhaven National Lab. And I think she is probably going to come back to China at some point of time. And then the nickel catalyst supported on nitrogen-doped carbon nanotube was done by my former postdoc Zhongbin Zhuang, who just went back to Beijing University of Chemical Technology as the Young Thousand Talent Program awardee. And the work was supported by Upper E and a Department of Defense Mirai program. Well, with that, I thank you all for your attention. I'll be happy to answer any questions you have.
Thank you. Very exciting talk. Thank you very much.
Thank you.
So last graph, you compared PAM, right, with your alkaline system. Why not experiments? Just here is simulated.
Yeah. So when you have these non-precious metal catalysts, it's not extremely trivial or anything to make a good MEA out of it. So I have one PhD student whose thesis has been completely on making MEAs using commercial membrane and platinum catalyst just to study the MEA structure. So the hope is he will get that pathway opened, and then we can just transfer this one and then get it done. So he has published a recent paper demonstrating we can get to 760 plus milliwatt per square centimeter performance using platinum and commercial membrane. But the other one is just done, and so I guess we will be doing it shortly. Yeah.
Next talk.
Okay. So the voltage drop is just due to the membrane limitation, right? It's limited by the green curve drop down rapidly.
Yeah, so mostly this is just a simple IR drop. So starting here, there's some mass transfer limitation. Yeah, this is mostly.
For the current, yeah.
Another question is for the ammonium and the phosphonium, why the trend is just the opposite, right? When you put the electron donating.
I don't think I know the answer. I think my chemistry knowledge is still limited. Yeah. A very good question. I had it. Yeah. I think some simple, a standard package and just do a calculation. I'm just not very good at playing that.
Well, phosphate might have this d orbital.
Right.
And
Yeah.
high electrons from aromatic group.
Right. I really think some simple commercially available package, if you put it in just sort of a DFT or something, probably you'll find the answer. I guess I'm intellectually a little lazy on that.
But the stability for the ammonium and the phosphonium, the degradation product, how do you look into this comparison for the ammonia?
Yeah, we have all those data. Yeah, so we captured all the products using NMR, so we have positive identification of all the products.
But there's one maybe I missed. You say the degradation product is something like phosphor with a double bond to something, right?
Right.
And you say there's no charge.
Yeah, there's no charge.
But
because
if you have a double bond, they also should be charged.
yeah, well, when I say charge, I guess we're literally talking a full positive charge. If you're really talking about like a polarization or having a partial, not exactly. I think I'm using charge in the most traditional sense of the word. You have a real positive charge. It's not like a dipole.
Very nice.
Yeah.
Actually, as I know, the hydroxides can be easily react with the carbon dioxide.
Yeah.
So in your experiment, how to prevent the interference of the carbon dioxide?
Right. So this is a very critical question. And the biggest advantage of a liquid base like KOH is actually they're going to bind with CO2 to produce bicarbonate or carbonate. So that has been the biggest problem for liquid-based alkaline system. And once you form that, it's going to precipitate. out. So it's going to damage the electrode structure and really destroying the fuel cell. The benefit of using a polymer electrolyte, bicarbonate will come, but they don't precipitate. So they don't irreversibly destroying the membrane. So this is number one. Number two, we do pay a price because carbonate has lower conductivity than hydroxide. So the internal resistance will be higher. But data out there by others show clearly if you have the operating temperature at 80 degrees C, you actually change the equilibrium much toward the hydroxide and CO2 gas instead of the bicarbonate. So the impact of bicarbonate formation on the cell performance is very limited, maybe 15%. So what I'm trying to say is there's no permanent damage, and there is a little bit performance reduction we might be able to tolerate. So
my second question is that related to the hydroxide oxidation reactions. Normally, the nickel can be easily oxidized into the nickel oxide. So can we consider this influence on the activities?
Yeah. So this is another very, very critical question. If you look at the last part of my presentation, I was basically saying what you just said. My nickel catalyst is not stable enough. If I stay within 0.1 volt, my catalyst can outperform platinum, but I can't afford to get the overpotential to a higher place, and then my one is going to going down because it gets passivated, but platinum doesn't do that. So engineering-wise, there is a possible solution. So maybe you get your loading high enough, so you make sure the overpotential on the anode doesn't get to that, but that's just harder to do, right? So for me, if I can someday come up a nickel catalyst, which is stable up to 0.3 volt, I think I'm pretty safe. Right now, I can't go that high. That's why I was showing you the simulated curve, 0.1 volt, 0.15 volt. It's very important for us to get the stability higher, and we have certain ideas. Yeah.
Actually, again, going back to your last, I really enjoy your very nice, beautiful lecture. The last slide that's showing the 3M, the PEM, polarization curve.
Yeah.
Actually, this curve depends upon the membrane thickness, right?
Yeah.
So in your simulation, how did you actually do this?
Yeah. So what we did in this simulation, I think we are limited by the contract. I think Tianshou actually knows. We just use the commercial membrane, standard thickness, and so you know the internal resistance and publish the conductivity. So we put it in there, and then if you look at the anode catalyst and the cathode catalyst, we take the literature data, so we know exactly the voltage current curve behavior. So it's a very simple simulation, But the short answer for the membrane, we use a commercial membrane behavior or data for that. Yeah.
In your view, is this alkaline? Well, you said your hydroxide membrane.
Thank you.
cell.
Yeah.
Sorry.
Yeah. I joke to my competitors. I say, if you give me $1 million or change the names, no problem.
So
but,
you wouldn't change.
If you're not giving me money, I'm not changing my name.
You think that the PEM's fuel cell, the hydrogen fuel cell will go away, so hydroxide fuel cell will replace it. So without changing the title, we still have the same thing.
Yeah.
Okay. So in your view, there's the problem. I think is really for one of the problem with the lithium-based fuel cell is still the proton conductivity is associated with the fuel loss through the system, right? Then there's a recent publication by the Imperial, not the Imperial, the Manchester group with the graphene being the proton conductor, right? So can you give some comment on that? This is a little bit beyond your presentation today, but then I would like to hear your expert view on that.
Right. So maybe I should be generous. So for me, if you look at the PEM fuel cell technology, I consider myself sort of trying to keep a balance between fundamental science and applied problems. I think I try to do both. I hope that came through in my presentation. I really feel we don't need to do much about Nafion anymore. I think it's sort of a done deal. It's okay. And if you look at the catalyst, we just need to make the catalyst more active. And I think right now the goal is actually getting the performance higher. I think there's a trend. You want to work at a very, very high current density. This is pure engineering consideration. If you can somehow move up the polarization curve to the higher current density, and you hope the amount of stuff you need will be smaller. So you may argue and say, well, you get higher current density, that doesn't necessarily save me money because the power is not maybe not the best place. What you need to keep in mind is if you can make this whole thing smaller, all the balance of plant, the bipolar plate, and the pump and everything. So right now, if you do the calculation, other things are becoming more and more important. So what I'm trying to say is, I think the shift of the PAM fuel cell research from the engineering point of view is a lot of engineering work needs to be done just to make things smaller so everybody else is becoming cheaper and the whole thing can fit into $30 per kilowatt. If you really look at the component, I think it's some form of platinum. If they can make it work, like dealloying, put it in, take it out without poisoning anything, and hopefully the stream will stay there for a long, long time, and the activity is much higher. So for me, that's why I more or less completely dedicating myself to the alternative. My hope is this is going to be the Gen 2, the generation 2 for the fuel cell engines. Yeah.
Thank you.